Hello folks, this week we're going to be looking at the Poisson distribution, and as it says here we're going to be looking at the properties of the distribution, how we use the Poisson tables and also the formula to find probabilities, and then we'll look at solving some reverse Poisson problems as well. So we're going to start just with a bit of revision. So if you look at this question, Stall invites people to try to shoot baskets. They're given 5 balls and win if they score with 3 or more of them. Jerry has a probability of 0.4 of scoring with each ball. What is the probability that he wins? So hopefully you recognise this as a binomial problem. So just pause the video, have a go at it for a bit of revision, and then I'll put the answer up. Okay, so hopefully this is the answer that you came up with. If not, it's probably worth just going back and recapping the binomial distribution at some point, although you won't need it for today's session. Okay, so in the binomial distribution, in this problem here, we're given a limited number of trials, so there was no way that he could score with any more than 5. Whereas sometimes we're interested in, as it says here, the number of times an event occurs in a period of space or time, and theoretically there are an unlimited number of times something might happen. So for example, we've got here Sam counts the number of cars travelling past her on a quiet road. X is the number of cars passing in 15 minutes. Shu uses a Geiger counter to record the number of particles emitted by a radioactive substance. X is the number of emissions in 1 minute. And Scott counts the number of people leaving a pub, where X is the number of people leaving in a 5-minute interval. So you can see that you're always given a limited amount of space or time. However, theoretically, for instance in example 1, there could be unlimited number of cars travelling down that country road in the 15 minutes. So what are the conditions then for a Poisson distribution? Well, X is all about counting the number of times that an event will occur in a given unit of space or time, but it has certain conditions for it to be a good model. So firstly, the events occur independently of each other and at random. So the fact that one event has happened will have no impact at all on whether another will happen. The events occur at a constant rate, so we can think of that as being proportional. So if it was the number of cars, for instance, in 15 minutes, then if we doubled the amount of time to 30 minutes, then we'd expect double the amount of cars. So they occur at a constant rate. And finally, the events occur singly, so that you can't have more than one event happening at a time. So some notation. Similar to the binomial distribution, this here says X follows a Poisson distribution, so we use PO short for Poisson, but there is only one parameter, and that parameter is the average number of times we would expect the event to happen in the given amount of space or time. Okay, so we're now going to look back at the situations that we considered a moment ago and see if we can decide whether we think a Poisson model would be a good model. So here, the number of cars passing along a quiet country road in 15 minutes. Well, we can assume that as it's a quiet country road, having one car go by is not going to have any impact on whether another goes by. We're not going to have 2 cars passing at the same time, so they're going to occur singly. So it looks like a Poisson could be suitable. The only difficulty might be is if the road was used by commuters or something at certain points in the day. It might be that certain times are more busy than other times, so the rate might not be constant. And also, if queues started building up, then if there's one slower car, it's more likely that other cars will follow. So in that case, it might not be independent. If we look at this situation, well, those of you that know about radioactivity might know that emissions do occur randomly, and this would follow a Poisson distribution. Finally, the last one here, well, if we think about the three conditions, people tend to go to the pub in groups or pairs, so it would be very possible that the events might not occur singly. You might have three people leaving at the same time, and also I would say the rate is not going to be constant, because as it approaches closing time you're going to get an increase of people leaving. So I would say that one's not Poisson. So if you're ever asked if the Poisson distribution is suitable, then think about those three conditions, so you will need to know those conditions. Okay, so the formula. Here's the formula for finding the probability that the event occurs X times. Okay, so we've got capital X, the random variable, small x is the number of times that we're expecting it to happen. And you can see here that it's got for x equals 0, 1, 2, 3 and so on, because we've already said that theoretically it could the event could happen an unlimited number of times. An example here, we've got x follows a Poisson distribution with 0.85, so that's saying we would expect on average the event happen 0.85 times, and we're asked to find the probability that x equals 3. So we can substitute that into the formula, and if you put that into your calculator, you should find it comes out to be 0.0437. Alright, so you're going to need to make sure that you know where to find the factorial button on your calculator. We could also be asked to find probability that x is greater than a number or less than, so inequalities. So if we were asked for this one, the probability that x is greater than 2, well, that would actually be difficult to work out as it is, because we know that x could happen an infinite number of times. However, all of those probabilities must add up to 1, so if we subtract the probability that x equals 0 and x equals 1 and x equals 2 from 1, then it will give us our answer. So we can substitute those numbers into the formula, work out those probabilities, and then simply subtract those from 1. Okay, so for that one it should come out to be 0.0549. So perhaps a more realistic type of question that you might get. On average, a call centre receives 1.75 phone calls per minute, so there's our value of lambda. Assuming a Poisson distribution, find the probability that the number of phone calls received in a random chosen minute is firstly exactly 4 and then no more than 2. And then for part B, find the probability that 6 phone calls are received in a 4-minute period. Now this is quite a common approach that A-level Poisson distribution questions take, because note that the time period has changed. So here we're given the average number of phone calls per minute, and here we're told that we're now looking at 4 minutes. So we'll talk about that in a minute. Okay, so for part for A part 1, exactly 4, we're just going to substitute 4 into our formula with the value of lambda as 1.75, put that into our calculator, and it comes out to be 0.0679. For no more than 2, well, that's the probability that x is less than or equal to 2, so we can simply add up these 3 probabilities. Okay, so work each one of those out and then add them up, and it comes out to be 0.744. Then for part B, well, we're told that y is the number of phone calls received in 4 minutes, or it's suggesting that we have this new random variable y, which is the number of phone calls received in 4 minutes. We know it was 1.75 per minute, and we know it follows a Poisson distribution, so the rate is constant. So in 4 minutes we'd expect 4 times as many calls, so that would be 7 calls in 4 minutes. So that is our new value of lambda, and we can say that y follows a Poisson distribution with lambda equal to 7. We are asked to find the probability that there are 6 calls, so we substitute that into the formula, and which should give us 0.149. That's to 3 significant figures. Okay, so an examination type question here. If you could have a go at this one, so pause the video, try it, and then we'll go through the answers. Okay, so we've got our value of lambda as 3.25. We're told to assume that a Poisson distribution is appropriate, and we want the probability that there will be 3 or fewer weeds in an area of 2 meters squared. So for this one, we have to first of all decide what the value of lambda is for 2 meters squared, so that's 6.5. And then find the probability that x is less than or equal to 3, so we're just going to add those up, and it comes out to be 0.1118. For part B, we've got to think back to the conditions, so we'd need to assume that the weeds occur randomly and that they occur at a constant rate. Okay. So with those types of questions, as I said, think back to the conditions. So in this question here, we were asked for the probability that x is less than or equal to 3, and we ended up adding up quite a few different probabilities. You might remember from the binomial distribution that when it came to working out probabilities like this, less than or equal to something, that there were other ways of doing it. So there are the binomial tables, and also there was the BCD button on your calculator, and similarly we have the same thing in the Poisson distribution. Okay, so there are tables of probabilities that exist for many Poisson distributions, and they give probability that x is less than or equal to some value of x. So here's a little excerpt. It would be crazy to try and have the tables for every different value of lambda. It's simply impossible, isn't it? So they pick out values of lambda that are likely to come along. And if you look at page 35 in your formula book, or at the back of your textbook, then you will find the Poisson distribution tables that will look something like this. Okay, so quick example of how to use them, although they work in exactly the same way as the binomial tables. So if we are asked for the probability that x is less than or equal to 4, for lambda equals 1.5, then we go to this cell here, lambda is 1.5, x is 4, and we can see that the answer comes out to be 0.9814. If we were asked for the probability that x equals a number, well, we could actually do that by saying it's the probability that x is less than or equal to 2 minus the probability that x is less than or equal to 1. So we've got lambda equal to 1.5, and we want 2 and 1, so we're going to take those two values there, subtract them, and our answer comes out to be 0.251. And finally, if we wanted greater than some number, well, we've got to remember that it's discrete. If it's greater than 1, that is everything except 1 or 0, so everything except 1 or less. And similar to the binomial distribution, you have to be really careful with those. Think carefully about which values are included and which are not. So for this one, lambda is equal to 2, and we want probability that x is less than or equal to 1, so y in this case, sorry. So it's going to be this value here, and we're going to subtract that from 1, so it comes out to be 0.594. Have a go at this question here using the Poisson tables and see how you get on. Okay, so fairly straightforward. First one, number of customers in a 15-minute interval. Well, we were given 18 in an hour, so that's 4.5 in a 15-minute interval, and we wanted probability that x is greater than 10. Well, that's 1 minus probability that x is less than or equal to 10. So use the tables to find that value, and then we've got our answer there. Okay. For x2, number of customers arriving in a 1-minute interval. Well, that's 18 divided by 60, so lambda comes out to be 0.3, and we were asked for the probability that x is equal to 2. So we could use the tables, or in fact we might use the formula for this question here. But if we're using the tables, it's these two values subtracted from each other to get 0.0333. If you use the formula, it should give you the same answer, of course. And finally, y, the number of customers arriving in an interval of length t minutes. The random variable y would have a value of lambda that's 18t over 60, or 18/60ths t, so 0.3t. We're told that the probability that y equals 0 is 0.2, so we can find that in terms of t by using the formula. Okay. And the good thing about this question is, because we're told the probability that y equals 0, then lots of these things cancel out. Do remember that 0 factorial is equal to 1, alright, and anything here to the power of 0 is 1, so in fact the probability that y equals 0 comes out to be this value here. Okay, and we're told that that is 0.2, so then we can take natural log of both sides and solve for t. Okay, so 5.36 minutes. Okay, if you were someone that liked to use your calculator, the ClassWiz calculator, to find probabilities for the binomial distribution, then you might like to do that for the Poisson as well. And basically it's very similar to the Poisson. You've got the formula, or the PD button, in this case Poisson PD, PPD button. They will find exact probabilities, or you've then got the tables and the PCD button to find less than or equal to. Alright, so it'd be worth trying to have a go at using your calculator to try some of these questions as well, so that you can decide what you prefer. Obviously we have to think about what working out must be shown, so if you're using the formula, then do make sure that you firstly show the distribution, the appropriate distribution with the value of lambda for the time or space that you've been given. Show the numbers substituted in, and then obviously you can just write down the answer. If you're using the tables or your calculator, then we know that they always are in the form of less than or equal to. So any problem you're given, you have to rewrite it in terms of less than or equal to, and then you can just write down the value from your calculator or the tables and find the answer. Finally, a reverse Poisson problem. We're told here in a call centre that there is at least one call going out in 88.92% of 1 minute intervals. So that's with a probability of 0.8892. What is the probability that no calls go out in a particular 1 minute interval, and what is the average number of calls going out in each 1 minute interval? So first of all, if we've got at least one call going out in that many 1 minute intervals, or that percentage of 1 minute intervals, then hopefully you're happy that 0 calls would go out in the remainder, so with probability 0.1108. Okay. And this probability that x equals 0 is always really handy, as we saw in the last example, because if we know the probability that x equals 0 is some value, then we can substitute that into the formula and we end up with just e to the negative lambda is equal to that value. Alright, so again we can take natural logs of both sides and we end up with the value of lambda 2.20. Okay, so hopefully that's helped get you thinking about the Poisson distribution, and you'll be all set to have a go at some questions in the lesson. Okay, thanks, bye bye.